So my name is Qemu. I'm your moderator, track host for today. And as usual, we have to thank the sponsors, Science Center, Google, Microsoft, MySQL, Oracle, Intel, SUSE for making FOSSASIA possible. So the next speaker, and now we have a double bill, but we're doing the first session now. The next speaker is Bandan. He works for Red Hat. And the title is the Qemu KVM ecosystem, navigating the code. So briefly, have you ever wanted to understand how Qemu and KVM work together? Wanted to contribute to KVM and Qemu but didn't know where to start? So Bandan is here to help. This workshop is a fast deep dive into KVM and Qemu code base to better understand the interaction between them. He will cover important functions of KVM followed by Qemu. Although the ecosystem extends way up above Qemu and KVM, we'll limit our discussion to the lower layers only. So Bandan is a software engineer in the virtualization group at Red Hat. Okay, it's a good time to start.
Okay. Hi everyone. My name is Bandan. I meant to make this as a workshop so that we could go over the code, but I don't know, things got messed up. So what I'm trying to do is explain a little bit on KVM, and then the next section is on nested virtualization. And then if there's time, then we can probably go through the important parts of the code. I don't think it makes sense to kind of do a demo on these things because there's a lot of information online. So this topic is about Qemu and KVM, or the associated components that make up the Linux virtualization stack. So that's the figure that I have tried to point out. The KVM and VFI. KVM is for virtualization, VFI is for device assignment, and they are not the only things that are part of Linux virtualization. The reason I mentioned them here because they have the same mechanism through which they work, which is they expose a device file to Qemu, and Qemu utilizes services from them through these device files. So we have our host hardware on top of which we have the kernel modules, KVM and VFIO, which expose device files. And then on top of which we have Qemu, which is the user space program. And on top of that, we have a management API, which is libvirt. I don't know of any other APIs that probably are out in the wild, but as far as Red Hat is concerned, we use libvirt a lot, and there are a lot of OpenStack users of libvirt. The reason for the management API is to just abstract some of the Qemu complicated command line switches and so forth. And the user land tools like Virt Manager, if you have a KVM user, you must have used Virt Manager, which is the graphical user interface. So they are built on top of libvirt. So whenever we talk about any hypervisor, we tend to ask this question: how is this different from anything else? So KVM is part of the Linux kernel as a kernel module. So it's able to use a lot of the functionalities of the kernel, such as scheduling low-level memory operations. And there's also a lot of networking user space to use, such as logging tab interface in the user space. And KVM guests are essentially user processes. So you could do a PS and see that there's a KVM process running, which you can kill as a regular user. And so KVM implements the mechanism. If you have had a chance to read the device drivers book on Linux, you must have read about the policy versus mechanism. So many pages of discussion. Although it's not entirely true, but I mean that's what KVM tries to do. It implements mechanism and lets Qemu kind of implement the policy on what to expose to the guest. So when we talk of KVM, we are mostly talking about the CPU side or execution. For I/O, most of the stuff is actually emulated in Qemu, but there are exceptions like vhost is a in-kernel virtualized network interface. There's VFIO, of course, for device assignment. So these show the traditional methods for virtualizing x86. Of course, the first one, which is the oldest one, is binary translation, where you trap and you kind of emulate the instructions so that your host OS can understand. Then there's the Zen approach, which is CPU virtualization, where you kind of get help from the guest as well to implement things that could be kind of a guest-specific CPU ID and such. And the last one, which is more recent, is hardware extensions. There are a lot of different architectures now with virtualization hardware extensions. We are talking just about x86. So SVM is for AMD and VMX is for Intel. And this is what KVM uses for providing virtualization services. So again, this is specific to Intel or VMX, but of course you can kind of think of the same thing in terms of SVM as well, which is AMD's parlance for virtualization. The way you enter virtual mode operation, virtualization operation, is you use an instruction called VMX on, which is x86 Intel specific. I don't know why they didn't decide to make this a standard. This is AMD has a different instruction, Intel has a different instruction. But anyway, the workings are the same. So VMX on switches the CPU to enable virtualization, or what we call as guest mode. And then VM launch is the instruction that lets you enter guest mode. So once you execute VM launch and then let the processor point to any instruction, that instruction is actually executed in a hardware-constrained environment, or a sandbox, if you may, which is called guest mode. And and then the real operation goes back and forth between the guest mode, which is the virtual machine, the guest that's running. And sometimes there has to be an event that needs to be managed that you cannot actually kind of handle in the virtual sandbox. So you have to exit out of it, and then you have to enter the host back to the host that is actually launching you. So that event is called a VM exit event. And once the host actually takes care of the event, such as an interrupt maybe, so host can again use this instruction VM resume to go back to guest mode and then continue with executing the guest. So and all these things are all are associated with a very important data structure, which is called VMCS, which is the virtual machine control structure. Again, this is Intel specific. For AMD, it's called VMCB, control block, virtual machine control block. So what is this VMCS? This is a memory region, which is something that you give to the processor where it can manage its data with respect to the guest and the host, because it needs to go back and forth, right? So, and you need special instructions, right? VM read and VM write. Again, with Intel you need the special instructions, but with AMD you can just directly use load store memory operations. And these are the instructions that let you manage the VMCS. VMPTR is to load the VMCS into the processor. RST is to reset. Clear is to clear the VMCS contents. Launch is to launch the VMCS as in the guest that's being managed by this specific VMCS. And if you want to take divide the VMCS into specific portions, then they have 5 parts, which is the first part is the execution controls that lets you decide what kind of features are exposed to the guest, or what kind of features are actually used to run the guest. For example, there's hardware enforced page table translations called EPT. You can set those bits in the VMCS parts of VM execution controls so that the processor uses EPT to launch the guest. The guest save state is the state where the state of the guest is saved once you are out of the guest and running the host for some reason to take care of an event. Similarly, the host save state is something that saves the state of the host when you are running the guest, and when you have to come back to the host, you kind of load this state and then run the host again. The exit controls define under what conditions you need to exit out of the guest. For example, you could say if there is an interrupt from an external source, like an external device, then we need to exit out of the guest so that the host can handle it. So that is defined here. And the entry controls define the environment for the guest. For example, whether the guest sees a 32-bit machine or a processor, or if the processor is in long mode, or things like that.
So, Bandan, the instructions for AMD and Intel virtualization, are they the same?
No, they're different.
So does it mean you got two code paths for different processor types?
Two different,
Oh, okay.
So if you use if you're on an AMD system, you have to load a different kernel module. If you're on Intel, you have to load a different one. So with that, we can take a quick look at what happens when you launch a KVM guest. So the first thing to do so that we Qemu and KVM can work together is have a set of common IOP tools, which is implemented by KVM and understood by Qemu. This is not entirely correct because KVM KVM is the only IOP tool you use with dev KVM file, the device file, and then that gives you a special FT that you can use to create, or manage the guest. So once you use KVM KVM, that gives you a special FT, which is, synonymous to like a guest as far as KVM is concerned, and then you use that device file, special FT to, run these IOP tools. For example, create vCPU will create virtual CPUs for the guest. Exit IO is essentially an event, but I don't know why I put it there. It's not an IOP tool. Set MSRS is an IOP tool. So when the guest tries to write an MSR, for example, this is through this specific IOP. KVM run is something that will be called by Qemu when the guest is to be actually run. So this all happens because the functionality is implemented for these IOP tools is implemented by KVM. So it's a tightly knit family. I mean, it's not something that will just work. You have to make sure that Qemu and KVM understand each other. And then of course there could be differences in versions, and then there could be new stuff that's being implemented. KVM could implement new stuff, and then Qemu might not know about it. Qemu could try to use new stuff that KVM doesn't know about because you're using a outdated kernel. So we have we also have an IOP tool called check extension, which is supposed to be used by all user space, including Qemu, when you are running a guest. So this basically asks KVM if you know about certain stuff, and then if KVM replies back saying that yeah, I know about this, then you are supposed to use it. If it doesn't, then you are not supposed to use it, or you are just going to play it out with an error message. This is the typical command line. I'm sorry it's not visible, but basically it says Qemu drive file is equal to guest.ing, and then SMD2 CPU host M1 gig MPC device, whatever PCI. So this is not a complete command line, but what I'm trying to show is the parts of the Qemu command line that are handled by KVM and the ones that are handled by Qemu. So all the I/O over here, for example, the VIRTUALIZATION BLK, which is the disk device, and VIRTUALIZATION net PCI, which is the network device. These are emulated by Qemu. They are paravirtual, so that they have a corresponding device driver in the Linux kernel of the guest, that is. And this line over here, MPC, is the machine type. The machine type is basically what the guest sees in terms of the machine. This maintains guest ABI, and one of the most common uses of it is migration. So if you are migrating, then you have to maintain a machine type. M1 gig is the memory. So KVM, Qemu use slot-based MMU, which are basically arrays of, fixed number of arrays for each guest. And once you specify the amount of memory to the guest, these arrays get configured accordingly to what part is RAM, what part is reserved, what part is ACPI, and all that stuff. So then these slots actually maintain addresses in host virtual addresses. And so they map the guest physical addresses to host virtual addresses. And then we had SMP2, which means that we are supposed to create 2 vCPUs for the guest. The vCPUs are basically the execution contexts that are run by KVM. And then once everything is set up, the KVM run that I showed you in the previous slide is actually called, so that these SMP execution contexts that were created, the vCPU contexts that were created, are actually used to run whatever code you give to it in guest mode. In this case, it's Qemu giving the address of the BIOS in the guest to start executing, just like you would do any x86 system. And that's how the system, that's how the guest runs. And then at this point, the guest is running, and everything is fine, but not quite, because we also spoke about the events called VM exit. But before we get into that, in short, if you write a very simple user space for KVM, so that you are able to launch a guest or a user space Qemu type hypervisor, if you will, which depends on KVM. So these are the steps that you need to follow. First of all, you need to create a VM. This gives you an FD that is corresponding to a VM struct in KVM that is maintained by KVM. Then you do a set user memory region IOCTL that basically sets the amount of memory that you give to the guest. This over here, create IOQ chip, is basically telling KVM to emulate an interrupt controller in the kernel. And we will talk about what's the advantages and disadvantages of having an interrupt controller in the kernel. Then we have create vCPUs, which creates the vCPUs for the virtual machine, basically the execution context. These are called when you want to set the MSRs in a specific setup for the guest, or the registers, the MSRs, whatever things that need to be set. And then finally you call KVM_run, which actually runs the guest. So at this point, you can, if you're on a classic like a uniprocessor system, you could think that everything is fine. The guest is running in guest mode on the processor that's on your hardware, but that's not enough, because as we discussed, we need to handle events, and those events cannot be handled by the guest, because first of all we don't want it to, because the guest is running in a constrained space, and of course also it's running constrained, so that's why it cannot even access some of the things that probably it would need to handle those events. So that's why we have the VM exits. VM exits happen all the time. There are so many VM exits, and most of the work right now, once everything has been stable, is to kind of reduce the number of VM exits, because the lesser the number of VM exits, the more performance you're going to get out of your virtual machine execution. So why VM exits? Because of course, as I said, if you are on a uniprocessor system, which is now not the case anymore these days, but if you are, then you also need to run the guest and the host at the same time. You are just not gonna. It's meaningless to just run the guest, because the host isn't making progress. How are you going to even interact with the guest? So both of them need to get scheduled in and out. So the host OS needs to run too, and then special operations like MSR writes or handling external interrupt. You press a key on the keyboard, what happens? That has to be handled by the host. So this all needs a VM exit, where the host kind of takes the handles the event and then decides everything is fine, and then jumps back into the guest execution again. And then the way it works is it's actually like this. It's simply like a while loop where you're running in guest mode. Something happens, an event happens, you handle it and then jump back to the start of the loop. Sometimes, there are cases where, specifically with I/O, for example, you are using, a paravirtualized network device, and you have to send a packet. KVM cannot do it, so you have to exit back to Qemu. Qemu takes care of the network packet and then jumps back again to KVM. So, so that's Qemu and KVM. I just put a single slide on libvirt, which is on top of Qemu. Most of the, most of the things like OpenStack, Overt, whatever you can think of, the virtualization stacks, they primarily interact with libvirt because this is the one that kind of abstracts away the complications of Qemu, not having to remember so many command line switches. And then the tools like Virt Manager, etc., built on top of libvirt. Libvirt stores its guest or the guest config as a XML file. You can either write it by hand or you can use Virt to kind of create it. So that's about it for libvirt, and I think with that, my next slides are about nested virtualization, which is the next topic. So if you have any questions right now, we can talk a little bit about them, and then we can jump to nested virt.
So just now, did you say that the guest is a single process?
No, I was just giving an example. That if you have a host where you just have one processor, and you put the processor in guest mode, you cannot do it in forever. You have to come out of guest mode because you have to handle some operations of the host too, because the host has to make progress too. You cannot just run the processor in guest mode forever. That's what I wanted to say. But in the real world, we have multi-processor systems, and a single vCPU or the single guest execution thread kind of jumps all around. It's handled by the Linux scheduler. It's not on a specific processor until you actually pin it to a specific processor.
So if a guest assign multiple virtual CPUs, like if you look at the host, right? How many processors will there be?
If you look at the host, the host does not see processors. The host basically sees execution context. Like there's if you know about kthread_create, which creates kernel threads, the host is basically going to see multiple threads. Those threads are actually visible in the guest as vCPUs because of Qemu. Did I make it?
So those threads belong to one process, or
they can jump all around. They don't have to be stuck to a single processor. So right now it could be on CPU 1. The next instance something got scheduled. So thread 1 is not running on CPU 1 anymore. Now the scheduler, the Linux kernel scheduler on the host, schedules it on maybe CPU 3. The guest doesn't know about it.
Okay, but in the case of KVM and Qemu specifically, right?
Yeah.
Would the scheduler try to do NUMA optimization?
Oh yeah, it would. Yes. If you have auto NUMA or anything enabled, which is the default, it's going to do that. Yeah. Anything else? Okay, so.
But I don't know. Maybe we should start. We wait until.
Like wait for 2 minutes and then start.
Yeah, because someone might want to come in for the nested.
Yeah. Okay.
So we start at 2:40. See if anybody joins.
Yep.